Hi everyone. Welcome to Vodcast 16. We are continuing through Chapter 5, and today we're in Section 5.2, which covers the topic of momentum. If there's an overlying sort of a principle or idea about Chapter 5, which of course is finite control volume analysis, it's really using some of the great laws of physics, dynamics, and solids, and sort of applying those great laws to fluids. And what we see is that all of the physical principles that are in place for other types of systems are also in place for fluids. So in other words, mass is conserved, energy is conserved, and momentum is conserved. So we're going to talk about linear momentum, make that application to a system and a control volume of a fluid, and see what that looks like mathematically. All right, so to begin, if we start thinking about the principle of linear momentum, I'll talk about it for a minute in terms of how we derived this equation for a system that involves solid particles or discrete particles rather than a fluid. One of the underlying principles of mechanics, of course, is that force is equal to mass times acceleration. And we know that acceleration is dv dt. So we can say that the force, a force vector, is equal to mass times the rate of change of acceleration, or the rate of change of velocity with respect to time, times the mass. And if we consider it for a system, we may have more than one force. And so we need to sum those up. And we also need to recognize that these are vectors. So we need to take into account the directionality of the forces and of the velocity or acceleration in this equation. Now, another way to think about this, if we separate this equation, we can say that the summation of forces times dt, and this is referred to as an impulse, the force times time, is equal to mdv, and mdv is the change in momentum. Now, momentum, which previously was designated by the variable L. That is not the case in this book, but I'm drawing some connections so that if you've had this in physics or in dynamics, that you may be able to see some of these correlations. If we integrate both sides of this equation, and if mass is constant, we can say that F delta T is equal to m delta V, or we can say that impulse is equal to change in momentum. Now, when we think about this in terms of a fluid system, we know that we need to decide how we're going to look at this mass term. It's very simple when we're talking about solids. We just have a block and it has such mass, or we have a wire and it has such mass. But for a fluid, are we looking at it in terms of a system? Are we looking at it in terms of a control volume? Or are we going to use Reynolds transport theorem and look at both, or the connection between one and the other? And so the answer is that for a fluid, we begin by the material derivative, and we recall that a mass per time is a mass flow rate, and we could also say that mass is equal to a density times a volume, and that a mass flow rate is equal to density times a volumetric flow rate, which is Q. So, in terms of a material derivative, we can say that ddt for the system of the velocity times the rho times the dv, so in other words, velocity times mass, so that's a linear momentum, will be equal to the summation of forces acting on the system, recalling that that is also a vector. This looks a little strange, so I'm going to just correct that. All right? So this is a statement of momentum equation from Newton's second law applied to a fluid system, or a collection of particular particles of fluids. All right, so to explain this in terms of English, we could say, in general, the time rate of change of linear momentum of a system will be equal to the time rate of change you see this? Yes. Of the linear momentum of the contents of the control volume plus the net rate of flow of linear momentum through the control surface. Okay, so that's sort of a statement of Reynolds transport, isn't it? We can look at the materials derivative and look at the relationship between what's going on in the system and what's going on in the control volume in terms of what is passing in and out of the control surface. So mathematically, we can write that as the material derivative, I should put system down here, of the integral over the system of velocity times density times the differential volume is equal to the partial derivative with respect to time in the control volume of velocity rho dv. Remember, we have to distinguish. I'm going to write this down here just in case. V vector is velocity. V slash is volume, right? Plus the stuff that's passing in and out of the control surface. And so we have two V's there, don't we? Two velocities. And this is just Reynolds transport theorem substituting momentum for B and velocity for little b. All right. So that's just a very, very general statement. So if we have a control volume that is fixed and non-deforming, this is a very general statement. So this is a somewhat general statement. A fixed, non-deforming control volume. Then we can approximate Newton's second law by eliminating some of the terms. Okay, so we have this plus what's going on in the control surface through the control surface. Is equal to the summation of forces acting on the contents of the control volume. right? So that this equation is a somewhat combined form of Reynolds transport theorem and the statement that we made earlier about the nature of linear momentum. All right, now I'm just going to write, your textbook covers this beginning on page 221. And if we look at page 221 in the textbook and scan down a little bit, you'll see that your authors go through this explanation, and we always equate this back to the second law. It does a very good job. And now we're going to talk about the application of linear momentum. And this is basically, the picture that they draw here is a vein where we have water squirting out of a nozzle, and the water is moving along the vein, and the water is exiting or leaving the vein at some angle theta due to the shape of the vein. So they've drawn the control volume around the vein, and you can see that the water enters here and exits here, so that the velocity, the mv, the linear momentum of the water going in, is all x directional, but coming out we have a different angle, so we have some x and y stuff. What that means is we have reaction forces. Force A, force on the vein, in the x direction, force on the vein, or the reactive force in the y direction. And what it really means is that if we have a net force imbalance, or if we have a net momentum imbalance, that this vein is going to move, isn't it? So the component of momentum up here is going to have to be offset by a force term of analogous dimensions in the y direction. And if the force component, or the momentum component in the x direction here, is not completely offset by the x component here, then we're going to have a movement of the vein in the x direction. Now, there are a few other things that we need to think about when we talk about linear momentum. The linear momentum equation must be satisfied. But also an energy balance has to be satisfied. And also the material balance, or the mass, must be conserved. So just because we're working with linear momentum does not mean that we don't have to work with this. Now, the one thing that we can remember is that linear momentum is a vector, but energy is a quantity, and mass conservation is also quantity. So all of those things have to be satisfied in those different ways. So we're going to work a problem in a little bit that sort of shows you what we're talking about. And I chose a problem in the back of the textbook that will be helpful to thinking about all of those ideas when you work a problem. Now, skipping ahead a little bit in your textbook, I've moved ahead up here to page 229. And what you see on page 229 and 230 are some very general but important things to remember when you're working a problem that involves linear momentum of a fluid system. And there are actually 9 different points. So I'll go through them rather quickly with you. But number 1 says when the flow is uniformly distributed over a section of the control surface, the flow into or out, the integral operation is simplified. So that's just a matter of the math. A lot of times, the way these equations work is you start with the most general form of the equation, and then based on the situation, you simplify by removing inconsequential or consequential terms, or removing terms that are not applicable. So, for example, what I mean by that is if you have a water hitting a vein and the control volume is moving but not deforming, you take out any sort of anything that has a dV in that sort of control volume then would remain constant. It would come outside of the integral. So simplifying is always dependent upon the system itself. And it's just really important to remember that, because otherwise you can make yourself crazy with these huge, sometimes unsolvable equations. Part 2 just says, or point number 2 tells us that linear momentum is directional. So we need to remember that that's a vector form. And now this is sort of an interesting thing. The flow of positive or negative linear momentum into a control volume involves a negative V dot n product. Now you recall we've been working with this a little bit with Reynolds transport theorem. We've been working with the V dot n with the Reynolds transport theorem. And we know that that just means perpendicular. But what happens when we have linear momentum is if this is our input, our inlet, and this is our output, our V looks like this, and the V dot n over here is negative. The V dot n over here is positive, right? So what that means is, if you think about it, like if you have V going in this way, and you have, let's just say that you didn't have the V coming out here. You didn't have the water stream coming out here. If you have V squirting into something, it's going to move in this direction, isn't it? All right. So in other words, you're going to have an unbalanced force system. So what it's really telling you is that mathematically it's because the angle is 180 degrees. But functionally what it's telling you is momentum in this direction will produce a force in this direction unless it's opposed by a reactive force, whatever the nature of that is. So to keep your sign straight, you need to remember that water coming into a system has a negative sign, and that water coming out of a system has a positive sign in terms of the momentum. The fourth point, the time rate of change of linear momentum of the contents of a non-deforming control volume is 0 for steady flow. The dV term is going to be 0, and so the whole term is going to go to 0 if the flow is steady. And the momentum problems considered in this text all involve steady flow. That's extremely important for you computationally. The reason for that is, quite frankly, at this level, we really get into an area of math that becomes, a lot of the equations become pretty unsolvable. Now, if you have had differential equations, you'll know that there are just a lot of differential equations that are unsolvable, and this is a group of equations that tend to be that way. But any time that we start looking at ways of solving groups of equations, it's referred to as computational fluid dynamics, okay? And computational fluid dynamics, although it often involves an equation called the Navier-Stokes equation that we will get into later, but computational fluid dynamics are really taking groups of equations or classes of equations and solving them for particular instances. And because the math in fluid dynamics tends very often to be unsolvable, this is still an area where research is occurring. So we have other ways of attacking equations that are not analytically solvable, but at this stage of the game, eliminating the terms or simplifying the terms that can be eliminated or can be simplified is very important. So it requires a certain amount of engineering analysis. But the point being made here is that the momentum problems considered in this text all involve steady flow. Remember that it's a gift that you can use to solve problems in this text from this point forward. And when you get a little bit farther along and you have more math, you may be solving some problems that don't exactly look like that. But for now, don't worry about it. All right, point number 5. If the control surface is selected so that it's perpendicular to flow where it enters or leaves, the surface forces exerted at these locations by fluid outside of the control volume will be due to pressure. Okay, that's another simplification. So it's almost always a good idea to choose your control surface perpendicular to the flow of fluid, so that V dot end product is a little bit simpler to break down. Point number 6, the forces due to atmospheric pressure acting on the control surface may need consideration, but often it doesn't. Often you're going to have the same atmospheric pressure on both sides of the control surface, or on the control volume, or on all sides, so it actually can eliminate it. It actually is often eliminated. 7, the external forces have an algebraic sign, positive or negative. We talked about that a little bit. Only external forces acting on the contents of the control volume are considered in the linear momentum equation. That's exactly the same thing that happened when we were talking about solids, whether it was in physics or in dynamics. It's just a little easier to isolate when you're talking about physics or dynamics or a solid object rather than a fluid flow, but it's exactly the same. Number 9, the forces required to anchor an object will generally exist in response to surface pressure and or shear forces acting on the control surface. And that's just saying that when they talked about the forces on the vane and they called it F sub A, they're just talking about anchoring force. We have previously called these reactive forces. All right, so in your textbook there are a lot of really good examples of problems that will help you. And I'm going to work a problem from the back of your textbook, which is problem 5.57. I'll bring this up. And it's a fairly simple problem to work. If you look at it for a few minutes, you'll actually see the solution, I think. If you've worked with momentum at all, you'll see it pretty quickly. But it brings up a lot of questions and brings in a lot of ideas. For example, conservation of energy, which we've not directly talked about in this section, but that often becomes important. And it also brings into question the idea of conservation of mass. So we're going to take a look at this problem, 557, in your textbook. And we'll not only solve it, but we'll also talk about some of the things that are being brought up by this problem. All right, so 557 is over here, and it says water flows steadily into and out of a tank that sits on a frictionless wheelbase, as shown in 557. Determine the diameter d so that the tank remains motionless if F equals 0. So what's happening here? We have water being added to a tank from this pipe, which has dimension or diameter small d. The water flows into the tank, and it comes out of 2 outlets at the bottom, possibly. One is diameter little d, same as this, right? The other is diameter capital D. And what they're saying is we have wheels here, and we don't want it to move. We want this force to be equal to 0. So what we're really saying is we want the momentum associated with the water here being equal and opposite in direction to the momentum of the water associated here. Now if you think about it, if you were to block this, if we were only to have this outlet, the small d diameter, what's going to happen? Well, the water's coming out of here, the water's coming in here, is pushing the tank to the right. And what that means is we would have to have some reactive force here unless the momentum here is essentially equal to the momentum here. But in this case, we have the possibility of water coming out this way. So we could have a momentum where the water coming out this way would push it in the opposite direction. So what we're doing is we're looking at what diameter do we need here if these two diameters are equal and the force is equal to 0. So we'll start with those ideas and we'll start working out that problem, and as we work through it we're going to come out with some other issues that we need to discuss as well. Okay, so 557, tank, spigot, diameter small d. At the bottom of the tank, 2 spigots. Sorry, this is kind of weird. I didn't draw that very well, but this is diameter big D, diameter little d, so this and this are the same. Water coming out here, water coming out here, and a force here, which we would like to be equal to 0. All right, now if we draw our control surface, I'd like to use a different color pen, I think, for this. If I can find one quickly. Here we go. All right. We have water coming in here. So I think it would be a wise choice to draw our control volume or control surface around the tank and at the exit points and pretty much at the entrance point of that of the, hang on a second, let's just try to zoom in a little bit here. There we go. You can't really tell, this is actually green and the rest of this is in black, but that's okay. So what we're saying is that the control surface then has this water passing in, this water passing out, and this force acting upon the control volume. So if we set up our equation, and it's steady, and so we have that one term that goes to 0 that we talked about in the points, but we can look at what's passing through the control surface, and in terms of momentum, we can write this form of RTT in this form of the linear momentum equation. All right, so we have that through the control surface, that the velocity times the rho times the velocity dotted with n dA is going to equal the summation of forces in the f direction, or the summation of forces in the direction. And we're told that we want that force to be equal to 0. So what do we have then? We have 3 places that we need to look at. We have water coming in at 1. We have water going out at 2. Scoot this over. And water coming out at 3. And we talked about the diameters are constant and everything is perpendicular. So V dot n, we talked about this is negative, right? The V dot n here is negative, but the V dot n here and V dot n here are both positive. All right, so we need to break up this integral into the 3 discrete points at 1, 2, and 3. So we can say minus, this is at 1, V1 rho 1 V1 A 1 in the most general sense. And if you look at 2, this would be positive, but it's backward. In other words, the velocity has a direction in the negative x direction. So we can write that as negative V2 rho V2 A2. And here we have a positive outlet and a positive direction. So that's positive V3 rho. And I'd really, well, let's say, since it's water, rho 1 equals rho 2 equals rho 3 equals just rho. So let's get rid of our subscripts there. We'll just call it V times rho. Here we have V3 rho V3A3 is equal to 0. All right? And so there's my expression for what that equation is going to look like for this control surface surrounding this control volume. Well, what else do we know? Not only do we have the equation for the momentum, we also know that mass has to be conserved. And we also know that energy has to be conserved. So what is the mass flow rate going in and out? We can say that the mass flow rate in at 1 has to equal the mass flow rate out at 2 plus the mass flow rate out at 3. All right. And another thing that we could say, well, let's just start with this. And we also know that the energy from the water here, which is an energy of position, I guess I'd say an m dot GH at 1, is going to become kinetic energy at 2 and kinetic energy at 3. And those are not directional, are they? All right. So let's go back and just work with this equation a little bit. Simplify that momentum equation. I'm going to come out a little bit wide again. Get a clean sheet of paper. Okay. So, starting with equation 1, let's just write it as V1 squared rho times area, which is pi d squared over 4, because we're assuming it's circular. Here we're going to have minus V2 squared rho pi times, in this case 2, we have d squared, capital D squared over 4, plus, it's plus because it's positive and it's coming out of the control volume, V3 squared rho little d squared over 4. And since the forces are required to be equal to 0, those three terms added together equal 0. So right now I've just taken this equation and simplified it in terms of bringing the v's together, since everything's perpendicular to the control surfaces. Written my signs correctly. That's have to be I've written the signs correctly now, and substituted in pi d squared over 4 for each of the areas, and recognizing that this diameter, are the same, little d, this diameter is different, big D. Okay. All right, now speaking of energy, what do we know? Well, we know that if we want to find the velocity at 2 and the velocity at 3, that they're going to be related to what's going on in terms of the water coming in. So if I just take a really quick look, I'm not going to redraw this, but the picture doesn't tell us what this height is, but we can just call it height. And what we can see then in terms of conservation of energy is that the flow rate coming in here has some potential energy, and it's going to become kinetic energy at the bottom. Now, kinetic energy is not directional, is it? In other words, it's not a vector. So in order to talk about V2 and V3, we could say m dot in times g times h, so this would be a power or a flow rate, is going to equal v, let's say m dot at 2 v squared over 2 plus m dot at 3 times v3 squared over 2. And if we just take one of these, we can say, let's just put these together, and we can say m dot in GH equals m dot at 2 v2 squared plus m dot at 3 times v3 squared, because the 2's will cancel out. And if V2 equals V3, which makes sense because they're on the same level and it all is a transformation of kinetic energy. So we could say m dot in GH equals m dot 2 V squared out, let's just call it out, plus m dot 3 V squared out. And further, due to conservation of mass, we can say that m dot in has to equal m dot 2 plus m dot 3, right? In other words, if this is a steady problem, if we are not accumulating mass in the control volume, then the mass that goes in has to equal the mass that comes out. Mass goes in at only 1 point, comes out at 2 points. So we can factor out our V out, and we can say m dot in GH equals m dot 2 plus m dot 3 times V0 squared, V out squared. And this is equal to this due to conservation of mass, so they cancel. And we get GH is equal to V0 squared, or V, it's not V0, it's V out, is equal to the square root of GH. And I've lost a 2 somewhere. This should be 2GH. So I'm just going to write a note here. Lost value 2. Okay. But this is just kinetic energy from potential energy. All right. So once again, when we talk about the conservation of mass, if rho is constant, then we know that the flow rate coming in at 1 is equal to the flow rate going out at 2 plus the flow rate going out at 3. These are volumetric terms, but we know that Q times, Q is in volume per time. And if we multiply that by mass per volume, right, which is density, so Q times density is equal to mass flow rate. Mass flow rate is conserved, so if density is the same, in other words, if we have an incompressible fluid, then we can equate the volumetric flow rates as well. And then we can just write out an equation for those. So we have a V1 times little d squared equals V2 times d squared, big D squared, plus V3 times little d squared, because these are the same on the inlet and on the one outlet. All right, now we also then know that V2 is equal to V3 is equal to 2GH. And so we get that V1 little d squared equals V3 big D squared plus V3 little d squared. Okay, so if you look at this equation, along with V1 squared d squared, this is what I got before, equals V3 squared little d squared minus V3 little d squared, or capital D squared. We can compare V3 to V1. And I feel like I need to put this picture back up again so that we can see what we're talking about. Okay, so we have V1, we have the inlet at 1, the outlet at 2, and the outlet at 3. So if V3 is less than V1, this first equation that I wrote down, hang on just a second. This is what we call equation 1. I actually did it up there. This is equation 1, 3. Okay, so if V3 is less than V1, that means that 1 is not true, can't be satisfied. If V3 is less than V1, equation 2 can be satisfied. But this eliminates it as a possibility, doesn't it? Okay. So then let's look at another case. If, on the other hand, V3 is greater than V1, 1 can be satisfied, but what happens to 2? Then 2 cannot be satisfied. So once again, that doesn't work. So what's the only way that it's going to work? V3 has to equal V1. It can be satisfied. 1 is okay if capital D is equal to 0. 2 is okay if capital D is equal to 0. So going back to our picture, what does that mean? It means that all the water here has to come out here in order for this to be equal to 0. And that means that this has to equal 0. So the conclusion we can draw then is capital D, in other words, the outlet at 2, is equal to 0. No water comes out at D, or at 2. And in order for mass to be conserved, if this is a steady flow problem, for D at 1 to be equal to D at 2, all of the water in at 1 comes out at 2. All right. So the solution to this is really a little bit trivial, isn't it? What we've really found is that in order for this to work at all, we really only have one outlet for the water, which is at the bottom at little d, and that big D has to be equal to 0. So big D in no way implies that the water, that outlet is bigger. It just means it's different, and that the outlet at 3 and the inlet at 1 are the same size. But the reason I present this problem to you is, first of all, if you looked at this, if you inspected it, and you realized that the outlet here is the same size as the inlet here, how can you have water coming out here based on mass flow rates? It can't happen, can it, unless we are discharging from this tank. In other words, unless we fill this tank up and we have more coming out here than we do here. The other thing is that the momentum in this direction and the momentum in this direction are going to have to be equal to each other in order for this force to be equal to 0. Otherwise, we're going to have to apply force. If there was more momentum coming in here, for example, there would have to be some sort of a force applied here in order for the tank to remain motionless. And the last thing that I like about this problem is that you have a potential energy, an MGH type term, associated with changing into a kinetic energy, which is a v squared over 2 term down below. And that's the only way that we can get that to work. All right, so there's some good principles in that problem, even though the math turns out to be a little bit trivial at the end. So that's it for section 5.2. And if you are finished with 5.2, we'll go on to 5.3. 5.3, we're going to talk about conservation of energy using the first law of thermodynamics. So those of you that have thermo under your belts will be well prepared. And the rest of you will catch on really quickly. So, see you next time.